Students, so today we continue with our thermodynamics and electrochemistry. Now we want to look at Gibbs energy and equilibrium in chemical reactions. So Gibbs energy is related to the position of equilibrium in a chemical reaction. Let's consider the example where we have a reactant A, converting to B in an equilibrium situation, and of course the equilibrium constant is given by the activity of the product B over the activity of the reactant A. And activity is really the active concentration or the effective concentration of a species in solution given by the product of activity coefficient and concentration, as you can see over here. Now, A is the equilibrium constant, and of course, like I said earlier, A are the activities. The position of equilibrium can be shown to be related to the value of the standard free energy change for the reaction. One can reason that a reaction such as this, starting with pure A or pure B, will proceed until it reaches equilibrium, and that the equilibrium position will occur where G of the system is at its lowest value. At equilibrium, the value of the free energy change for the system will be equal to 0, and that is the free energy change of the system, not the standard free energy change, but the free energy change of the system. The argument concerning the position of the equilibrium and its relationship with G can be illustrated by the following diagrams, where you have the free energy of A decreasing, right? Decreasing as it goes down to give you the product B. So the free energy of B is lower than that of A, and then you have the equilibrium position there closest to B. Now, if you should say G, the free energy of B, right, which is GB minus GA, which is therefore products minus reactants, then you'll get a negative value because the free energy of the product is lower than that of the reactant. So when you say GB minus GA, which is product minus reactant, the free energy of product minus reactant, you'll get a negative value, and this indicates that the reaction is spontaneous, because we discussed previously that whenever the free energy change for a process is negative, this indicates a spontaneous process. This tells us something. It means that the equilibrium position lies closer to the product side for a spontaneous reaction. Of course, it does not mean that all reactants or all of the reacting species have been converted to products, because in an equilibrium situation, you'll always have a mixture of reactants and products, but the equilibrium position lies closer towards the product side. That is, you'll always have more products than reactants in a spontaneous reaction. In a non-spontaneous situation now, what you have is a situation where, as you go from reactant A to product B, the free energy increases, and so when you go to say free energy of the product minus the free energy of the reactant, in order to get the free energy change for the process, you will end up with a positive value. This is a non-spontaneous situation, because we know that free energy change for a process being positive indicates that the process is non-spontaneous. Again, this does not tell us that none of the reactants have been converted and none of the reacting species have been converted. In this situation also, what is indicated is that what is clear is that the equilibrium position lies more towards the reactant side. Yes, you will get some amount of conversion of reacting species to products, but you will have a lot more reacting species remaining in your reaction vessel than the amount of product reaction being equal to the standard free energy change. There's a relationship between Gibbs free energy change and the equilibrium constant, and this basically can show you how, or allow you to use rather, the Gibbs free energy change to calculate the equilibrium constant, and since the equilibrium constant is related to the amount of uh, products, or the concentration or activity of products to reactants, and this is something significant. Now, the actual relationship between delta G and the position of equilibrium is given by the equation here, which tells you that the free energy change at any stage of the reaction is equal to a standard free energy change, delta G naught, plus RT ln Q, where Q is the reaction quotient. The reaction quotient is just the ratio of the activity of the product or products raised to their stoichiometric coefficients over the activity of the reactant or reactants raised to their stoichiometric coefficient. Of course, like I mentioned, delta G naught is the standard free energy change for the reaction. Now, at equilibrium, the free energy change for the reaction is equal to 0. So this equation here, delta G naught plus RT ln Q, will be equal to 0. And so what we find is that delta G naught, which is the standard free energy change, is therefore equal to minus RT ln K, natural log of the equilibrium constant, of course. Now, you could rearrange that expression and get to calculate K, but before, let us just define a few things. Equilibrium constant is equal to the ratio of the activity of the activities of the reacting species raised to their coefficients over that of the the product actually over the that of the reacting species, the activities, of course, raised to their coefficients. We have the quotient, the reaction quotient is calculated the same way. It is the activity of the products raised to their coefficients over the activity of the reacting species raised to their coefficients. So you realize that equilibrium constant and reaction quotient are calculated the same way, basically from the same equation. So what is the difference? Reaction quotient is when the system is not at equilibrium, right? It is basically at any stage of the system, and it is continuously changing. That is the thing, because if you look at the quotient, it is activity of products over activity of reactants raised to their coefficients, right? Now, during the reaction, the activity of the products will be increasing, whereas that of the reacting species will be decreasing. So the reaction quotient is continuously changing throughout the progress of the reaction. The equilibrium constant, though, is not changing. The equilibrium constant is fixed at a fixed temperature. So that's basically where the reaction has reached a stage where the rate of the forward process is equal to the rate of the reverse process. And so you're basically at a stationary point. Nothing is changing. All right? So that's the difference between reaction quotient and equilibrium constant. Now, this equation, delta G naught is equal to minus RT ln K, can be used to calculate the concentration or pressures of substances present at. Let's consider the reaction. This reaction where we have nitrogen gas combining with hydrogen gas to produce ammonia gas, which is a very important reaction in our daily lives. For example, ammonia gas we know is used to prepare ammonium nitrate, which is used for fertilizer. So it's a very interesting system to investigate or to discuss. We want to find K. So let us try to find K, or to see how we can find K for such a system. Of course, K is the equilibrium constant, which can be expressed as the activity of the reactant of the product actually, which is ammonia gas in this case, and we are going to look at the activity of ammonia gas squared divided by the product of the activities of the two reactants. Of course, for the hydrogen gas, we have to cube. We have to have a cube because of the reaction stoichiometry. Of course, we know A, as I said earlier, represent the activity of the species or species in consideration. Now, there are some things that we must know in seeing that we are dealing with activity or using activity, which is quite an important parameter. For solids, for pure solids, the activity is 1 for a pure liquid. Activity is also 1 for a gas. The activity is calculated from the ratio of its partial pressure to standard pressure. And for solution, for example, for 1 molar solutions, these are referred to as standard solutions, and so the activity basically works out to be 1. Now back to this ammonia system. Of course, as mentioned, the equilibrium constant is given by this expression here. Now, using the definition of activity of a pure gas or of pure gases, we know that it's the partial pressure of the gas over standard pressure. And so what we have done here is to basically just replace the activity with what activity means for gases. And this is how we end up with this expression here. Now, K is obviously unitless since the activity terms are basically unitless. Now let's say for the combination of nitrogen gas with hydrogen gas to give ammonia gas, we have the enthalpy values. We have the enthalpy value, I should say, and we also have the entropy value, where the enthalpy, standard enthalpy change for the reaction is minus 92.2 kilojoules, whereas the standard entropy change is minus 199 joule per Kelvin. Now we can use this equation here, which says that the standard free energy change is equal to standard enthalpy change minus the product of the thermodynamic temperature and the entropy change for the process. And using that equation, now we can calculate the free energy change. Now, if we have the free energy change, there's this relationship, the Boltzmann relationship, which basically connects the free energy change, the standard free energy change that is, to the equilibrium constant. So delta G is equal to minus RT ln K, and that's a relationship which connects free energy change, standard free energy change, to the equilibrium constant. Now, using that first equation, delta G is equal to delta H minus T delta S. All right, we use that equation here, and we can calculate here the free energy change, the standard free energy change for the process, which is minus 32.92 times 10 to the 3 joules. Now, back to the Boltzmann relationship. We could use that to basically find K, which is the unknown in this equation here. ln K works out to be, or natural log of the equilibrium constant works out to be 13.29. If we do the exponential E, if we do E of which is the reverse of or the opposite of natural log, then we can get the equilibrium constant, which is 5.91 times 10 to the 5. Now this is an interesting value. The fact that this value is larger than 1 indicates to us that the equilibrium constant, right, which is a fraction, right, it means that the numerator of that fraction is larger than the denominator. Because remember the expression for the equilibrium constant. Here it is, and here is a simpler version. So if seeing that this value, which is the value of K, is larger than 1, it indicates that the numerator, that is, the activity of ammonia gas, is larger than the product of the activity of nitrogen gas to hydrogen gas cubed. In other words, the numerator of the fraction is larger than the denominator, which simply means that we have more product in place in our reaction vessel than reactants. That is, the equilibrium position lies more towards the product side. This is a spontaneous reaction. And you could have realized that from the value of the standard free energy change, which was negative. So that is just one way, just by looking at the equilibrium constant, that you could draw some conclusions. Now, the usefulness of Gibbs energy, or Gibbs free energy change, as we discussed some time ago, is that it allows us to predict spontaneity, and we don't need to calculate the change in the entropy of the surroundings and combine that with change in entropy of the system. It is quite convenient to use Gibbs free energy change then. It also gives us an idea, because it is related to the equilibrium, so it gives us an idea of the equilibrium. So it says related to the position of equilibrium in a chemically reversible system. All right, and it also gives you an idea of the maximum energy which can be obtained from a reaction. Now we want to move on, as we discussed in class, to look at electrochemistry or electrochemical systems. And electrochemistry is basically built on top of thermodynamics. There's a relationship between them, a relationship that cannot be covered up. So let's say, for example, we're looking at a system, and just to mention, numerous chemical reactions involve the transfer of electrons between the reacting species, and that's why electrochemistry is very, very important. It is also the branch of chemistry which deals with our ability to develop systems like cells for the storage of electrical energy. Now, let's say we're looking at a system where you have a solid piece of sodium metal, and that piece of sodium metal is exposed to oxygen, exposed to air, which contains oxygen. What you will find is that after some time, the sodium metal will be covered with a white powder. That white powder is sodium oxide, right? As a result of the sodium metal surface becoming oxidized. Now, what has happened there? What took place? What has happened is that the sodium metal atoms would have released their valence electrons, right? So one sodium atom will release one electron, all right, and that one electron would have been transferred to an oxygen atom. Of course, oxygen forms two minus ions, and so what you find is that two sodium atoms now would have to come together to release two electrons, such that one oxygen atom can pick up those two electrons to form the two minus ions. And that is how sodium oxide, that white powder, is formed. Now, this can be very, very useful. This can be very useful, as we will mention now. In terms of observing electrochemical processes, you have seen this before. For example, if you have a solution of copper sulfate and you should immerse a piece of zinc metal in that copper sulfate solution, what you will observe over time is that the zinc metal will start to become black, whereas the copper sulfate solution, which is characteristically blue due to the hydrated copper ions, will start to become colorless. What is going on here? Now, what is happening is that the copper 2 ions, the aqueous copper 2 ions, are being converted to copper solid, right, which is deposited on the surface of the zinc metal, that black substance. And of course, you probably say, no, but copper is pink characteristically. It's pink. The metal is pink. Of course, but in the presence of oxygen, you could also end up with things like copper oxide, which is black, and other substances. So you end up with the copper being deposited on the surface, and further oxidation or reaction with oxygen, you end up with copper oxide, which is black. Now, the zinc, what is going on is zinc. The zinc metal would have been oxidized now to zinc 2 plus, producing 2 electrons, and those 2 electrons were the electrons accepted by the copper 2 ions. And so this is our overall, so you have an overall cell reaction where zinc solid is converted to zinc 2 plus, whereas copper 2 ions are converted to copper solid. That's a redox process because the zinc is oxidized from zinc 0 to zinc 2 plus, whereas the copper 2 ions are reduced from copper 2 plus to copper 0, which is copper solid. And that is important. That is an important reaction, as we will see shortly. And what is interesting about this reaction also is that it is spontaneous. So once you immerse the zinc metal into the copper sulfate solution, then you will have reaction. Now, this is what you call, this reaction is called galvanic displacement. And this brings us to the fact that we have two types of electrochemical cells. You have the galvanic cell, which is also called the voltaic cell, and we have the electrolytic cell. The galvanic cell differs from the electrolytic cell in that in the electrolytic cell, what you have is a non-spontaneous reaction being driven by the input of charge, whereas in the voltaic or galvanic cell, as it is also called, you have a spontaneous or you have a spontaneous reaction taking place leading to the output of charge, or you could say then a spontaneous reaction takes place and in so doing produces a flow of electrons, which is called an electrical current. Now, what happens at the electrodes? What happens at the electrodes? And this is quite interesting. Now, let's say you have a piece of zinc metal, and if you think about what a piece of metal is just a lattice of ions held together by a sea of delocalized electrons. So, for example, now, if we're thinking about a piece of zinc metal is just a lattice of zinc ions arranged in an orderly fashion called a lattice, as mentioned, held together by a sea of delocalized electrons. And these delocalized electrons came from the valence shell of these what were atoms and are now existing as ions inside the lattice. Now, the same thing goes for the copper. So let's say you immerse a piece of metal in a solution of its salt. For example, you immerse a piece of zinc in zinc sulfate, and that zinc metal is connected to a piece of copper metal which is immersed in a solution, copper sulfate, for example. What happens is that at the zinc electrode, which is the anode, what you have is a situation where zinc ions inside the electrodes break off. In other words, they come out of the electrode and they enter solution. When they enter the solution, they leave their valence electrons inside the anode. These valence electrons then cause the anode to bear an overall negative charge because of the presence of these excess electrons, right? These excess electrons will travel around an external circuit. They will travel around an external circuit over to the cathode. Now, before we talk about the cathode, let's continue on the anode. When the zinc ions break off and enter solution, leaving behind their electrons, this is called oxidation because they lost their electrons by leaving them inside the anode. So this is oxidation occurring at the anode. All right. The electrons that migrate over to the cathode will build up on the surface of the cathode. So one would expect that the cathode surface will eventually become negative. However, copper ions in solution, right, will diffuse to the surface of the cathode where they will collect these electrons. That is, they will remove electrons from the cathode, and this will cause the cathode to then bear a net positive charge. However, when these copper ions collect electrons from the cathode, they become reduced, and so they end up sticking to the surface of the cathode. So one thing that will happen is that the cathode will start to increase in size. Alright, the cathode will start to increase in size as a result of zinc ions being reduced on its surface, that is, being converted to a solid on its surface and therefore are unable to flow. So they get stuck to the surface of the cathode as a result of being reduced. Now, that in itself is interesting because if you are removing positive ions from solution, right? Because remember, starting out the solution was neutral in terms of charge. But if you're removing the positive ions, leaving behind the negative ions, then what you find is that there will be an overall buildup of negative charge. Because remember, starting out the solution was totally balanced in terms of charge. But you're removing the positive ions and leaving the negative ions in solution. So a solution at the cathode, which is what we call the cathodic or the cathodic solution, will become overall negative in terms of charge. That is a problem. Let's go back to the anode. At the anode, right, where oxidation is occurring, there is a movement of positive ions into the anodic solution. The fact that there more positive ions are entering the anodic solution, whereas the amount of negative ions present are constant, then the anodic solution will therefore become net positive. This is also a problem. So the cathodic solution, right? The cathodic solution becomes net positive, the anodic becomes net negative, the cathodic solution, whereas the anodic solution become net positive. That's an issue. Cathodic solution net negative, anodic solution net positive. That's a problem. How can we solve? How can such a problem be solved? Well, if the two solutions are connected by a salt bridge is simply a device, or it's something that basically connects the two solutions. But the salt bridge, as the name suggests, is made up of a salt, or a salt solution. A salt is really a combination of negative and positive ions. For example, a good salt to use is like potassium chloride or potassium nitrate. Potassium chloride and potassium nitrate ions are, those two ions, potassium ions and nitrate ions, or potassium ions and chloride ions, tend to move really fast. And so what you find is that the chloride ions, which would be the negative ions in the salt, will migrate towards the anodic solution to neutralize the buildup of positive charge, whereas the potassium ions, if we're dealing with potassium chloride, would migrate towards the cathodic solution to neutralize the buildup of negative charge, thereby allowing a charge balance in the two half cells. So the salt bridge is very important in connecting the two half cells electrically, and allowing a salt a balance, right? A charge balance between the two solutions. So this is very very important for us to note. Now, just to mention, you have what we call the Daniel cell, which is, this guy is like one of those early guys who basically designed this a cell. And the thing is with Daniel was using a porous spot instead of a salt bridge, and this cell had some problems because of what we call liquid junction potential, as a result of different diffusion rates of the ions. So though this cell did not have a salt bridge, we must say that it worked. It produced a nice potential. However, it suffered from liquid junction potential as a result of the difference in diffusion rate, or diffusion constant for zinc ions versus copper ions. And so what you find is that at the interface between the zinc sulfate solution, which is inside the porous spot, and the copper sulfate solution, there was a buildup of negative and positive charge. And so this, of course, this limited the potential coming out of the cell. Of course, the other things here are just for you to, are like notes you can read. I will basically discuss all that we wanted to in this presentation. Thank you.